Professor Tomas Recio doesn't need much introduction. He's a very famous person, at least in the community of computer algebra, and he has a lot of fans. I can see a few of them here in the participants. He's from Spain, and he does a lot of work with GeoGebra, which is also a software that many students are familiar with. He's going to talk about a real mechanical geometer. Professor Recio, please go ahead.
Okay, can you hear me well?
Yes.
Okay, so thank you for the invitation. And yes, my talk will be about a real mechanical geometer. It's something quite different from the previous talk, the kind of content, but I think it has to do with algorithms in a very deep form. So this is a little bit the sketch of my talk. I hope we will have time to touch each of these items. The first of all is about dynamic geometry, the concept of dynamic geometry, then automatic reasoning, then the algebraic geometry and computer algebra algorithms that are involved in this real mechanical geometer, and then the impact in mathematics education and some open questions. So first of all, a quick mention to what is dynamic geometry. So dynamic geometry, we refer to some software that allows you to, say, display, to make constructions, to make geometric constructions. But it is very important to remark that it is not about plotting. So here in this window, you can see two constructions of a square. This first construction is just approximate. We have 4 points. We make the segments. And this is not a dynamic geometry construction. This is just a 4 points and 4 segments. What is a real dynamic geometry construction is to take 2 points, then the segment, then the perpendicular, then the circle. So you need to make a construction so that if you drag one of these points, then the whole figure will keep being a square. So this is dynamic geometry. It's not plotting, it's not design, it is geometry. And one of the most important famous dynamic geometry, dynamic mathematics software is the software GeoGebra that has over 100 million users all over the world. So it's a very relevant software. And in the context of mathematics education, we have a lot of resources for teaching, over 1.6 million public resources. So these are data from 2023. We have not more recent data. You can imagine what is the situation today. So for the web page with resources is this one here. Let me show you just one of these public resources. These are public, all of them. So let me show you this one, for instance. Here you have this. This is made by the creator of GeoGebra Discovery, Professor Markus Hohenbarter from Linz, and this is one of the constructions you can do with GeoGebra Discovery. This is a typical. This is some artist work from the Netherlands called Theo Jansen, and the problem for the students is how to replicate, how to make this moving this way. So it is a very surprising task, a very interesting task in general. So let me show you again. Let me show you again some of these resources. So we are working with a fork version of GeoGebra. So what I'm going to show you is not about GeoGebra itself, but about a variant of GeoGebra. GeoGebra is free, and this variant is also free, freely available. You can use it in cell phones. You can use it in laptops. You can use it of course, in computers, and you can download it from here. So this is what we call GeoGebra Discovery. There are several variants, several versions of this GeoGebra Discovery. You can download all these versions freely from all these links that you have over here. So GeoGebra Discovery is a version of GeoGebra that is specialized in automated reasoning. So let me start with automatic reasoning with some relation between automatic reasoning and geometry. Let me say that the first time, in my opinion, that someone tried to make a machine that in some sense was a mechanical geometer was 1959, somebody called Gelertner that made, he was working for IBM, and he was doing some machines to prove automatically in those days geometry theorems. So this is some of the statements made by this Gerlertner in 1959. So it was the first attempt. This is the statement he was trying to prove, and you can see you need to prove that this is a parallelogram. I am not going to go into details because you can have these slides available. I will send the slides to Amir so that he can distribute the slides for you after my talk. So you have this statement which doesn't look like easy to prove that this is a parallelogram, and then this is what we do right now with GeoGebra Discovery. So in GeoGebra Discovery, we make this construction, this quadrilateral ABCD, and then we make the construction here. I am not going to detail. And then I ask the machine, please tell me what is the relation between these two lines? And the answer is the two lines are parallel. Remember that the problem by Gelertner was to prove that this EFGH was a parallelogram. So in particular that the line EF and the line GH were parallel. So here, when we ask the GeoGebra Discovery about the same question, the machine automatically, even in a mobile, in a cell phone, answers you, telling you this is true, they are parallel. What is important here is that the machine says that not because they look parallel, not because they are numerically close to being parallel, but what the machine does is to think mathematically, rigorously about this statement, and the answer is yes, they are parallel. So this is if we ask about the relation. If we know that they are parallel and we want to check it, we can ask something else. We can ask proof that they are parallel, and the machine answers yes, it is true. So we can ask for the relation, the machine discovers the statement, what is the relation, they are parallel, or if we have already the relation, we can ask, please prove that they are parallel, and the machine answers yes, it is true. Moreover, the machine can show you the proof. So this is the beginning of the proof, given some arbitrary point, this is the polygon, whatever, blah, 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 then prove that they are parallel. And then start making the proof here, and you can see the proof, which is an algebraic proof, an algorithmic proof about the parallelism of these two lines. And at the end of the proof, it tells you what is the difficulty of the statement. So we have a definition of difficulty. The machine, this mechanical robot, can tell you what is the difficulty of the statement. Well, this is a quite easy statement. The difficulty is of degree 2. So you can see here the difficulty level. That's a very curious. So to give you an idea about what is behind this, this tool, let's say that if T is the thesis and the H are the hypotheses, so we say that the statement is true if the thesis holds over the components of the hypothesis variety where the variables, the free variables are really free. So in particular, we do some proof by contradiction. We consider the hypothesis, we consider the negation of the thesis, and we look for the elimination of this ideal over the free variables. And if it is different from zero, then we say that it is true. And if it's true, this means that 1 belongs to this ideal. And if we express 1 as a combination of the hypothesis and of the negation of the thesis, what we get is a kind of complexity measure. That means the degree of the polynomials such that 1 is a combination of the hypothesis and the negation of the thesis. This will be for us a kind of ranking of the complexity of the proof. So this is in particular for this statement. This is the statement 1 equal to 0. So the S1, S2, S3, S4, S5, S6, and S8 are the hypothesis, S9 is the negation of the thesis, and of course this is equal to 0, and then this is equal to 1 also. So this is a contradiction. So this is the proof of the statement, and the degree of these polynomials that appear here is the degree of the complexity of the statement, and you can see it's degree 2 because these polynomials are of degree 2 at most. So this is one of the results. This mechanical geometer can do some other things as well, very, very relevant. In particular, they can also prove inequalities. So for instance, here, I made a construction of a triangle, and I make a construction of the height of the height of vertex C with respect to side AB. So K is the height of C. So the area of this triangle is K times C. C is the side AB. So K times C divided by 2 is the area of the triangle. And then I ask, what is the relation between the area of the triangle and H is the radius of the circumcircle. So I have made the construction of the circumcircle by taking the bisector of AC and the bisector of AB. The intersection is D, so D is the center of the circumcircle and H is the radius. So I ask the machine, please tell me what is the relation between the area of a triangle and the radius of the circumcircle. So this is a question which is not trivial question, and the machine answers, please, K times C, so double the area multiplied by 2, is less or equal than 3 square root of 3 over 2 h squared, the radius of the circumcircle square. So you can see the statement is, the proof are not, statements are not so trivial. This is the proof. And let me show you some other. So for instance, there are some classical questions I am asking the machine to prove. Let me tell you again that this is not artificial intelligence in the generative artificial intelligence in the sense that the machine goes and looks for some proofs in the literature or in the database. The machine thinks algorithmically and makes the proof. So for instance, I take this classical inequality by Cesaro. The product of the sum of each side with respect to the sum of the two other is less than equal than 1/2. So I ask the machine to prove what is the relation between A plus B times A plus C times B plus C with respect to A times B times C, and the machine answers this. So as you can say, it's incredible. I am really surprised about the ability of the machine to prove classic statements. This is a classical book by Botima and et al. On geometric inequalities that is asking about, again, the sum of the sides of the triangle and the radius of the circumcircle, and the answer is, I asked about what is the relation, and the answer is 3 square root of 3 times the circle radius. So you can see it's really powerful. This is Ptolemy's theorem. So I give you a quadrilateral, and I ask, please, what is the relation between the product of the opposite sides and the product of the diagonals? So here, I want the machine to discover, not only to verify or to find relations that I have already made or constructed. I want the machine to be able to discover new statements. So here, there is no relation between F times H plus G times I and the product of the two diagonals, J and K. So there is no relation. So I ask the machine, please, I want to make a construction such that these two elements are equal. How should I place point C? And the machine says, you must place point C in this circle. So let's say that the quadrilateral must be co-circular for this equation to be true. This is called Ptolemy's theorem. So the machine is able to discover a missing hypothesis for a statement to be true. So this is even more relevant here. So this is a typical construction. This is typical problem of this book. ICMI is the International Commission on Mathematical Instruction, and in the 90s, some people from England wrote a book, a very classical book in math education, that is called School Mathematics, and they made the following question. I give you a square. This E and F are the midpoints of AB and BC, and D is the opposite side, and I make these lines, DF and DE, and the diagonal AC, and I want to prove what is the relation between AG and GH and HC. So I want to prove, really, the question is, prove that AG is 1/3 of HC. So right now, the machine, I took this classical problem, and I asked the machine, this is again GeoGebra discovery in one version called automatic geometer. So we can work with this machine automatically in the web page, automatically in the internet, and I make the construction A, B, C, D, and the point E, the point F, and then I ask the machine, please prove me all theorems you can imagine over this construction. And in particular, the machine says that AG is equal AG, this is the answer, AG is equal GH, for instance. So the machine is able to discover 31 theorems in 2 seconds. So this is another way of using this mechanical geometer. So another application of this automatic discover is the following. So this is a building, and I want my students to go around, take a picture of the building, place the picture on GeoGebra Discovery, and then start trying to find what is the relation between the height and the length of this window. And the machine answers is a square root of 2 plus 1. This is the ratio. So it's really impressive how the machine can, or maybe here this photo of a table, we can find that this is an ellipse of a certain characteristic. Let me show you again another application of this automatic geometer. This is a metro station in Spain, a subway station in Madrid. This is designed by an artist called Okuda, San Miguel. So I want the machine to discover what are these triangulations that appear here. So I put a photo of this wall on GeoGebra Discovery, and I asked GeoGebra Discovery, please tell me what is this triangulation, and the answer is it is practically 90% coincident with the Delaunay triangulation. Delaunay triangulation is a typical computational geometry construction. Let me tell you that there are very different number of triangulations, a very large number of triangulations over a set of points, but it is very strange that this artist Okuda and the Delaunay triangulation practically agree everywhere. So this is another example of Okuda. You see there are some difference, like here, this triangulation here, the one by Delaunay and the one by Okuda are different, but my mechanical geometer can practically be as artist as this man Okuda. This is Santander, where I am living now. We take a picture of this little viewpoint to the sea, and I want the machine to discover theorems about this construction, and the answer is incredible. This is the answer. This is all the theorems that the machine proves about this construction automatically. In 8 minutes, the machine has proved 2,500 theorems. So the question is, all these theorems, are they relevant? They are irrelevant. They are interesting. Which are interesting, which are not? Some of these statements are trivial. So, for instance, you are making a construction which is a regular, I think it's octagon. So it is obvious that FG and FE are equal. But the machine discovers this theorem. But other theorems are very new, very difficult, very relevant. So the question is, we need to have some tool to to measure the complexity of the different computations. So what is the interest of finding this, of ranking the complexity? So for two reasons. One reason is the cooperation between ChatGPT, so between large language model of artificial intelligence and our symbolic artificial intelligence, GeoGebra discovery. And the other reason is, of course, to make the automatic discovery of the automatic geometer to choose somehow the user can say, please tell me only results of some difficulty level. No, don't tell me all of them. Tell me just a few of them. So this is a very interesting, and this is some recent papers that we have done concerning this topic. In the first one, we check ChatGPT and the geometric locus computation, and we verify that ChatGPT makes a lot of mistakes, which is very normal. But what is relevant is that we can check with GeoGebra Discovery the mistakes of ChatGPT. So in some sense, we would like to establish a cooperation between ChatGPT and GeoGebra Discovery. So ChatGPT verifies what ChatGPT declares can be verified with GeoGebra Discovery. So in some sense, this collaboration could improve large language models performance. And the other thing is that, of course, as I said, the other thing is to prevent output of thousands of results. Some of them are very simple. So our future goal is to improve the performance of GeoGebra, in some sense, trying to prove only interesting theorems. We would like to somehow adapt GeoGebra reasoning tools to students with special needs. So for instance, if I am a teacher, I could say, please, this is, I am a teacher, I am for instance, one of the jury of a mathematical Olympiad, and I would like to verify that this statement is of a certain level of difficulty. I can ask GeoGebra Discovery, please tell me what is the rank of this statement. So this is some of the possible applications. Of course, providing benchmark for data science. These are references where we have been already, GeoGebra Discovery has been already mentioned. And as I say, for the collaboration between ChatGPT or in general, generative artificial intelligence. So here you have one example of this last consequence. This is ChatGPT, where we have asked one of these statements, what is the relation between a to the 6 plus b to the 6 plus c to the 6 and the in radius. So we ask the machine to prove this inequality. And so the ChatGPT starts asking, and it says, we have this inequality. Then I am not sure if this inequality is true or is false. So I would like to verify if this equality is true or is false, where A is the area of the triangle. So I could go to GeoGebra Discovery and ask, please tell me if this inequality is true or is false. It is verified using GeoGebra Discovery automatically. It says, yes, this is true. So you can see there is a lot of interesting results. And our proposal, our ongoing work right now is about this measure of difficulty, which is for us not the difficulty of the proof, because, well, proofs can be sometimes eureka, can be very simple after thinking a lot. But what is the difficulty in the sense of what is the relation between the expression of the thesis or the negation of the thesis and the expression of the hypothesis. So let's say if I have a statement with very complicated hypothesis, but the thesis is exactly one of the hypotheses, then this will be a trivial statement. If I have a statement which has very complicated hypothesis, but the thesis is very simple, this must be probably a very interesting theorem. So the importance is the comparison between the expression of the thesis and the expression of the hypothesis. So this is for us, I am not going to go here into details because this is perhaps too complicated. So here you have this Ptolemy's statement I told you before has difficulty of degree 7. So what we are doing now is to find algorithms, to study algorithms to find the complexity. So we have now one algorithm, but we would like to understand if this algorithm there is a better algorithm to measure the complexity, if this algorithm is mathematically invariant with respect to something called Gredner basis. So I am not going to enter into detail. I would like to go over the reals because all our proofs are over the complex numbers. We would like to establish also statements over the reals. This will involve inequalities. Right now, we do not have a proof involving inequalities. We cannot have a complexity measure of inequalities. So we would like to work in this context. And as I say, we have to do a lot of tests, and we would like to ask experts in computational algebra geometry about how to improve our algorithms. And as I say, this is initial work, and we would like to ask for the cooperation of the experts in computational geometry, both complex and real, for help concerning this complexity measure. And I think this is all. Thank you so much.
Okay, thank you, Professor Recio. I have several questions, but if anyone from the audience has a question, they can raise their hand. Otherwise, I will go with my own questions. Maybe I start myself. So maybe I start from the end. You said the complexity for the inequalities. So there are computational algebraic algorithms to deal with the inequalities such as cylindrical algebraic decomposition and quantify elimination, those kinds of things, which are over reals, right?
Yes.
Can that be something like the complexity of maybe, I don't know what algorithms are being used in GeoGebra for the inequalities, but if they are using CAD or something like that, maybe the complexity of that algorithm can be used?
Yes, I understand. Yes, that was my. Let me tell you that my initial, my dissertation was about real algebraic geometry.
Right.
So I know quite well about this topic. Yes, GeoGebra Discovery, this seemingly very simple program, has inside Tarski, a software that performs cylindrical algebraic decompositions. So this is the way in which GeoGebra Discovery says that the statement is true or discover geometric inequalities using cylindrical algebraic decomposition. But the problem is about how to measure the complexity. So to measure the complexity of inequality, I would like to. So let me say, when you have let me go to equalities again. Real equalities. You know there is something called the real Null-Stellensatz. You know this? Yes, real Null-Stellensatz. So you are an expert also in real algebraic geometry? Do you?
I do something about that.
Okay. So the real Null-Stellensatz, so the Hilbert Null-Stellensatz expresses that the thesis must be, a power of the thesis must be a combination of the hypotheses. So for me, the complexity of a statement should be the power of the thesis, the power of the thesis, and also the degree of the polynomials that the power of the thesis is equal to these polynomials multiplied by the hypothesis. So the expression of the thesis compared with the hypothesis, this will be for me, the degree of this will be for me the complexity of the statement when this is inequality. Over the reals, you know that the complexity, the real Null-Stellensatz declares that the power of the thesis is equal to a sum of squares plus, okay. So what is the degree of the sum of squares that appear there? How to compute the sum of squares? So this is not, that does not appear in the current literature. So giving a thesis and a hypothesis in the real setting a thesis that is true over the reals, I would like to have a measure, I would like to have an algorithm that gives me the squares and gives me the sum of squares with the lowest degree. So the lowest degree. I would like to find the lowest degree, and this lowest degree will be for me the complexity over the reals of one equality. So now imagine with inequalities, there are some positive Stellensatz. So the positive Stellensatz, okay, you understand the question. So this is open questions. We don't know.
True. Yes. Thank you for that. That's an interesting question. Maybe I will send some email and we can discuss that later. If no questions from the audience, I will go even more with my own questions. So, so the complexity of how finding these the truth value or those things goes to the algorithm, but from, let's say, coming back to the geometry theorem. So in calculus, we have a concept called elementary function, which we have a list of basic elementary function, and we say every other function that can be written as basic arithmetic or composite of these functions becomes still elementary, and then we make a boundary, elementary functions, non-elementary functions. Is there something formal for geometry theorems, elementary theorem, and non-elementary formally defined in the literature?
Yes. But see, let me say, it's a very interesting question. You are very interesting. So, thinking about elementary, so you are thinking, please establish some complexity related to the steps, to some basic steps, some basic steps that will be your elementary steps. Okay, so this relates the complexity measure of the statement with the complexity measure of the proof. These are different things. So I am working in complexity measure of the statement, not of the proof. But of course, what you are asking me is, this is something called, done in the 19th century by Lemoine, called geometrography. It was the way to see how many ruler and compass steps you need to perform to make some construction, let's say. Okay, so we can use this also, but of course our GeoGebra discovery, our mechanical geometer work with algebra, not with geometry. So in some sense, we could try to find a connection between the two of them. And there is a program called JGEX, Java Geometry Expert. This program, it approaches geometry statements in a different way. Approaches this with logic, as you say, with the steps. With now I conclude this, then I make this construction with the steps. Of course, what is the advantages? In some sense, this is closer to human intuition. What are the disadvantages? The performance of Java discovery is in GeoGebra discovery is infinitely much quicker and better and more deep than Java Geometry Expert. But anyway, so we are already taking our results and we compare with the tree of Java Geometry Expert solving the same question. And we compare the number of steps of Java Geometry Expert and our complexity measure. We are comparing the two of them. We have already published a paper on this topic. So it is very interesting. And we are also, there is another thing. We are also asking students and teachers, what is your impression? What is your intuition about how difficult is this statement? And we are comparing our algorithmic definition of complexity, the Java Geometry Expert definition of complexity as the number of tools, and the human intuition. And it seems that there is a quite close relation. But this is ongoing work. We are working right now on this.
Yeah,
Okay,
it,
that's
it
very
would be very interesting to see how that degree of that polynomial is getting connected with this number. And the number of steps in the logic format is not unique because you can go from different ways. So maybe taking a minimal or something is there, right? And it gets
yes.
updated if someone finds a shorter step proof. So yeah,
It's
maybe I
very,
ask,
very
but
yes. It's very difficult. I am trying to find a recent paper of mine which has this, which has done this, where I can show you, uh, where I can show you where this is done. Here it is. I think is. Let me show. I am going to put it in the chat if you want. Should I
sure,
put it in the chat?
sure.
In the chat. Okay, here it is. So this is automated analysis of the, I think it's open. Everybody can take a look at this. In the Annals of Mathematics and Artificial Intelligence. This is the automated analysis, and there is the comparison between Java Geometry Expert. I think so, if I remember well. Okay?
Okay, some more question. If anyone has a question, raise your hand. Otherwise, I think it's only mine until 9:45. So for the elimination that you're using, is it a Grosvenor basis with lexicographic, or there are some smarter things? Sometimes the resultant is faster, or some other method for elimination.
Open question, ongoing work.
Nice.
We are using the standard pure lexicographic, but we do not know if this is the best or not. We have asked questions to people in several conferences, several experts. Professor James Davenport, you know him, of course.
Yes.
Yes. We have asked people like Professor James Davenport on this, and we don't know. So our complexity measure depends on the Gerner basis, or does not depend. We don't know.
I see. Yep. And another thing about you said that you provide benchmarking data. I know one person who's not unfortunately here today, so the Rio, who was a student of Professor England. He's in
Yes.
the participants, was using some of the GeoGebra generated examples for I think CAD or SMT lib data set. Yes.
Yes, 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 yes. No, but our benchmark is concerning GeoGebra discovery in the sense of automatic reasoning. Okay, so it is, and we are measuring how difficult is, or how many the usual statements, what is the difficulty level, and well, we have found also statements of difficulty 30, 30. Uh,
Right.
Pythagoras theorem has difficulty 1. So you can imagine, and it's very interesting. We are taking problems from the mathematical Olympiads and compare the behavior of the teams, of the human teams, and the algebraic and the complexity of the statement. And there is a relation. When the statement is very difficult, the teams usually get less points. Very interesting. Okay, so very good.
Is it easy for a user to catch the calls to Grosvenor basis or to the CAD in the Tarski solver? Those calls getting collected. So for people who are working on improving algorithms to do the
Yes,
Grosvenor basis
yes,
computation, CAD computation,
yes. So
can
right
someone
now,
get the calls out and store them and then
yes,
work
yes. So
with them?
you're talking about the inside, no? How can you get the inside, isn't it?
Yeah, so for example, you put the geometry
Yes,
questions there, but
yes, yes,
whenever it is calling a Grosvenor basis or a CAD, that
yes,
can be saved on a different file, so
yes,
they can work with them.
yes. Every time you open GeoGebra Discovery in your computer, you also open automatically the terminal window, and the terminal window shows you all the steps of the machine. Now I call Tarski. Now I compute this Gremner basis. Now I eliminate. I do this. I do that. So you can follow this all the time.
I see. So
Of
it
course,
can be
you
easy
do, you
to
do
write a
not.
piece of code to capture those
Yes,
things from the
yes,
terminal.
yes, yes,
Okay.
Yes, but you do not need to do it. I mean, if you are a user, you are a teacher, you are in the school, you can forget about the terminal. But if you are a researcher, you can go to the terminal and look carefully about how this is going on. Yes, that's what we do.
Thank you.
Okay, I think
Any
I need
question
to.
from?
Yes, I
Yeah,
will have to
you're leaving?
leave.
Oh,
Yes,
okay.
I will have to leave because I need to leave at 10:45, so it's about
Okay.
the time right now.
Yeah,
Thank
sure.
you so much. It's very interesting. I am quite old, but for me it's surprising how a machine that I am the one that is I am programming it. I mean, not programming. I am the one that has the mathematical algorithm behind. The programming is made by people in Linz in the Johannes Kepler University, and it is incredible the output. I cannot believe it. I asked the machine, please show me theorems about this construction, and the theorems are impossible for me to understand, but they are true. So, and also we have, I can tell you that there is a paper, not by us, by people from the University of Strasbourg, in which they prove that formally this algebraic geometry approach is as correct as the logical approach. So it is not, we are not making statements about some algebraic constructions, but about geometry. So this is somebody called Narbou, Pierre Narbou, Pierre Boutry and Julien Narbou. They have made some papers on the formalization of Euclidean geometry. So it is very relevant for us. It's the basis of the rigorous of our approach. Okay. Thank you so much.